Hello YouTube viewers, welcome to my show Computer Wednesday. In today's episode, we're gonna take a closer look at supercomputer. So let's dive right into it. Well, first we have to understand what the heck we are talking about. Well, we are talking about a very specialized equipment. It's not something like a gaming PC or a video editing system. It's a very specialized. You have to know what you want before you even start to commission it, because the building time for these puppies are very long. Sometimes it can take upwards of 4 whole years. We were like, okay, we gonna build a supercomputer, so you start buying land, you start to figure out how the heck you're gonna get the concrete, because these computers are very heavy, and like all that jazz you have to figure out, and then you have to like, okay, how am I going to provide megawatts of power to this. So it is a very specialist equipment. On top of that, they are always built for a purpose. Even though this is quote unquote computer, each supercomputer is fine tuned for its need. Basically, some supercomputers are designed for weather application, so they will be built in such a way that they are fine tuning that application. Other would be built for, let's say, energy department, so there will be like specifically designed to handle large data set. Depending on your requirements, you can understand that each supercomputer is built for one task. They cannot just like, okay, I was working on this supercomputer, I will go to this supercomputer. Even though you might be going to a better supercomputer, you may end up getting lower performance simply because it's not optimized or fine-tuned for that. So it's a very purpose-built tool, and they are huge. I mean, like, they are really big. To give you a context of that, whenever somebody says, oh, they're thinking like, okay, this is a one room of it, there would be generally multiple room of these are like generally football field sizes, bigger than that if possible. So they're big, and in terms of power, they consume power in megawatts. They're like, yeah, we don't even talk below a few megawatts, like 5 to 6 to 10 megawatt. Right now everything is limited to that point. Like there is a very good chance some exaflop computers that will come, that exaflop being a unit, once we reach that, we might exceed that 10 megawatt power consumption. And these are large scale computer, like each itself is not a huge thing. Like if you see one of the unit, quote unquote, that's a normal computer. Like again, when I say normal, I mean commercial computer. It's not your desktop processor, but it's like it's something that you can understand. It's not that. So how the heck these make normal things make into a huge thing is basically it's large scale computing. It's simply way, think of it that way. You take a brick, you have nothing, you just have a brick, but you take thousands of them, you can build a wall, you can build a house. Same goes for supercomputer here. Basically each brick is a computer itself. So that's what it is. Now let's understand the workings behind this, whole demon. First thing, foremost thing you have to understand, because you are making like so many computer nodes, you have to have very good networking. Now that is the fundamental why supercomputers are nowadays possible to this extent. Because in early days, people wanted to use supercomputers, so they are like, okay, we're gonna make a custom silicon, basically a very dedicated chip, and then we're gonna mass produce that to like 5,000 pieces or 10,000 pieces, depending on your requirement. But that was ludicrously expensive, idiotically slow, and useless. Simply because by the time they started the design of the processor, made the processor, got the processor delivered in large enough number to start building the computer, commercial market would have already surpassed in terms of performance. So that was left very early on, and then now people started to use commercially available part. Basically you can just go and buy. So they are no longer like, okay, we're gonna build this custom processor. So right now there are like 3 applications you can have. Intel modern supercomputers that are being built now, like under construction now, they are using AMD Apex systems, and then there are IBM based processors that you never hear in local use. It's not something that you buy. I mean, like, you can buy that, but it's not something that you will generally hear. It's a third kind of processor. So you have AMD, Intel, and IBM. So IBM is also very successful in, like, they have like 2-3 supercomputers, top ranking supercomputers based on their processor itself. So it's a commercial product. However, do understand it. Like, let's say, to give you an example of what kind of commercial we are talking about, NVIDIA Tesla graphics card right now, it's not a graphics card, it's a compute card. Now these puppies are expensive. Can you buy that? No, because the moment you call up or send an email to them, they are like, your minimum order is 100, minimum order is 1,000. So these are not something that you can just go and buy, even if you have the money. So you have to have bulk order capabilities. Now topology wise, like, we do not just take one computer and connect it to another one. You cannot do that, because that would make a single point of failure. Like, if you make everything serialized, failure in the first link will kill all those things. So people generally do very different kind of topology. So generally they use cluster topology. So you'll have few in one group, few in another group, few in another group. So that's what you generally see. You will have different rooms, like like this room is like cluster 1, this room would be another cluster, or you may have racks, like this whole rack is one unit, another rack is another unit, so they have redundancy, failover, and easier management, because it's very difficult to have like raw data going from one compute node to another node, because that data is huge. Think of it this way: the data bandwidth between your processor and RAM, it's huge. It's huge. So you cannot tangibly do that like with one computer to another computer. You cannot have like processor talking to each other. That will take too much. So they will generally process the data to some extent where it's like compact enough for optical data transmission. Then they will transmit the data from one node to another node. So cluster topology is generally used. Now they consume data on such a level that they need their own server system, basically own data center, which may be, depending on design, they may have like a separate building that is just a server, or they may have like okay, these are the 5 compute nodes, one of the node would be the server node. So that's why I'm saying like they are never built like as a brick wall. They have always a kind of design purpose to it. And they need large power management, because you are talking about megawatts. The UPS that handles this kind of power loads, those UPSs are so huge, so high voltage, so high dangerous. Basically the people who are qualified to work on them, they have to wear like blast proof clothing, basically meant for high electrical arcs, because there's like 3000 volt, 10,000 volt and all that jazz. It's very dangerous to basically manage the power on that level. And then you have to understand the whole aspect. You are consuming megawatt. Basically in law of thermodynamics simply means all of the energy that you consumed will become heat eventually. So you start with, let's say, 5 megawatts of your power was consumed by your computer. That means you have 5 megawatt of cooling to do. So you need huge cooling units, like huge. So how these things are designed, basically in terms of how they're supposed to work, you have to understand that even though these are quote unquote computer, even though these are made by commercial parts, they each have different tasks in mind and different basically needs. Because even though, let's say, a supercomputer is built by, let's say, university, and that is like open for business, so to say, you pay them, you book a time slot, and they will allow you to do that. Even in those scenarios, they will specify, hey, our supercomputer is very good for physics modeling. Another computer will say, hey, our is very good for like large number crunching. Other will say, hey, our is very good for protein folding and all that, biology basically. So there are supercomputers that are built for that purpose. So you can have 3 core departments. You can have CPU based, GPU based, and huge RAM based. Basically I have provided the video down below which you should check out, and you will get the idea. Because CPU, while they are quote unquote inefficient, they are very good at random things. Like you throw anything at them and they're like, I got this. GPU, while very efficient, while very powerful, and while ludicrously parallelized, I mean, like all of these nodes could have like 8,000 processor nodes, parallel nodes. Those nodes don't have the oomph. Basically it's not a processor node where you're like, I can handle a whole operating system. These are like, you give me one thing and I'm going to do it amazingly well. So let's say for weather systems, these are awesome. But if you are talking about something volatile, let's say protein folding, processor people will use that. On top of that, there are certain applications that just need RAM, and you might be like, oh, how much RAM? Well, we are talking about 100 plus terabyte RAM. So you can understand. So they have to build a specific kind of computer server unit that is only made for that. Yeah, these things require huge amount of RAM. So they will be like, okay, just go into that part of the system. And generally they will mix the topology. So even if, let's say, somebody is building a weather system and they are like, okay, use all of the GPU system, they will still have a lot of processor built as a backups. Because let's say once the supercomputers get retired very quickly, because like let's say somebody built it, paid for it, and it's like they will be retiring it like 2 to 3 years basically. And when I say retire, I don't mean they will shut it down or deconstruct it. It simply means it's no longer the fastest as they wanted. So they will start to build another one, rent to something else, or something like that will happen. So in those sort of scenario, to utilize remaining life of the equipments, because these are commercial equipment, they will keep running 24/7 into 365 until like 5 to 8 years reliably. So people are like they still want to utilize something, but again, if they made it very specialized, they will be limited. It's like only we can do this. So that is why they are generally mixed topologies. What about the operating system? They are generally Linux based. Like there is nothing else, tangibly speaking, that can handle that. Even China's supercomputer runs on Linux. So these are the design aspects of it, behind the scenes, so to say. So then the question becomes, why the hell do we do this? Because these puppies are expensive. You are talking $200 million to $500 million. So this is not a joke. And not to mention, the running cost itself would be huge. So why do we do that? Well, a few years ago, like there was a craze of big data. Now, what does this big data mean? Simply means, think of it this way. Amazon, as of now, right now, me talking to you, have data points on 1 billion users. YouTube has 2 billion users. Google has 3 billion users. Like these are big bees, and it's not that okay, it has just your name and all that. No, it has a profile, psych profile on you built there. Again, can you do anything about that? No. Can a human do anything about that? Hell no. So to process that kind of data, to like process that terabytes and terabytes and terabytes of data, you have to have supercomputer. Otherwise, that data is just uselessly collected. So to handle that, to like take that mess of data, extract patterns out of it, make recommendations based on that, you need supercomputer to do that. So that is one big purpose on the commercial department. Another aspect that affects you directly is that it allows accurate weather modeling. Now, weather modeling, if you are familiar with 1990s, people used to like, okay, let's say this is the country map, and they're like, okay, cyclone is coming here. They will evacuate this whole area because they could not track it very well. Nowadays, we are like, okay, this is the hurricane. It's gonna hit exactly here, like, and only for safety reason they will evacuate a nearby area. But basically, think of it that way. From going to like this whole sector of country, you have to freeze because hurricane can hit it. We went to okay, this whole state, now we are at the point, this district should be like red alert, like we should be ready for something, because again it's still a dynamic system, so some things could still change. But yeah, like if we say it's gonna rain, it's gonna bloody rain. So we reached a point where it's very accurate. So how the heck that's happening? Because we have been collecting satellite data, large data, big data from all the NASA systems, all the ESA systems, all the ISRO systems for decades. Now processing that kind of information gives you pattern that you would never saw before. Utilizing that pattern, now you can reliably track some things. So weather prediction requires this. Another aspect is drugs, because nowadays we humans live very long lives, man. Like when India got its independence, people's life expectancy was like 30 to 50. Basically, it was not that you're gonna die randomly after 30. It's just that some infection, some minor disease, something will end your life. Nowadays, we are easily reaching to 70 to 90. Like we are touching there. Like I have seen people who are 90 plus olds, and many might even live to 100. So we live very long life. So our problem is our DNA itself is not an infinite machine. It will break down on its own, and we are very fast creatures. See, the only creatures in basically in nature lives that very long. It's very slow creatures like turtles, whales, things of that nature. Basically, if you are slow, you will live long. If you are as fast as humans, which are like we are as comparable as horses, we're not supposed to live very long, but we are living long. So our protein is like pushed to the breaking point. So we have to understand how the heck protein is working. Based on that, we have to make precise medication. Drug companies, some of the world top 500 supercomputers, some of them are owned by drug pharmacies, basically where they are running simulations on protein sequences and all that jazz. Astrophysics. Now, astrophysics is a thing that you simply cannot calculate on normal computer, because the moment you start to, let's say you want to understand what happens if moon leaves Earth, basically, which is living, because moon is going away like 1 inch per year. Now that may not sound much, because you have to understand the distance is in 1 light second. So 1 inch is like nothing. It's negligible. It's like 0.001. So you understand that, like, but again, still you have to calculate for that. Still you have to plan things in advance. Think of it that way. To send Voyager probes, we had to plan in 10 years advance. Nowadays we are thinking about sending things to, let's say, Alpha Centauri. That could take like 50-60 years. So we have to plan very far ahead. For those kind of reason, 1 inch every year, that matters. And not to mention, if you want to understand what happens when black hole collides, the amount of mass that we are talking about here is like in hextrillion, trillion, and some extra trillion, and then add some million on the top, and then it's like, yeah, that many tons. Normal computer will just it will roast itself if it tries to handle that kind of zeros. So we have to use supercomputer for that. Otherwise, it's just going to create a very low resolution voxels and give a very, very sloppy simulations. So large simulations also require large processing data factories, basically a supercomputer. So think of it this way: this is not a gaming PC. This is not something that you can remove from human civilization and have no effect. It will have drastic impact. Like it's a necessity tool. Like from every country that is like big enough, be it India, be it Nepal, be it China, every country is trying to build it or already has few of them built it. And these are not a sort of quote unquote show off pieces. These are actually useful tools. That is why we built it. That is why I spent this kind of money on it. So this was my presentation on supercomputer. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me your extra disappointment. Please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.